we are ready. What we have learned so far is how to represent information which is originally in the analog form to a digital form. Ultimately, this information is going to be transmitted on a channel in the form of a sequence of binary pulses. It could also be a sequence of what are called emery pulses. That is, you could have instead of representing the signal by a 2-level amplitude, you could also represent it by more than 2 levels by grouping bits of information together into a single amplitude. Maybe you could club 2 bits into a single amplitude with 4 possible levels and so on. But we will talk more about that later. In general, therefore, we are going to transmit on the channel pulse sequences with discrete levels, either 2 or more in number, right? So let's at the moment restrict our discussion to binary signals. So in this binary system, our information is in the form of ones and zeros, and any 2-level waveform is adequate to represent this ones and zeros information and then transmit it. However, there is an important question: what kind of waveforms to use and what are the implications of using various kinds of waveforms, right? For example, we could have some of the choices that I can just talk about without much introduction is what are called unipolar waveforms as an example. Then we could have polar waveforms, so-called polar waveforms. You could have bipolar waveforms and many others, which we will talk about in due course. A unipolar waveform will be one in which the 2 pulse levels are represented by, let's say, a 0 volt and a positive voltage, right? A polar one will be one in which a 0 represented by a negative voltage and a 1 by a positive voltage, or vice versa. A bipolar one would be a slight generalization of polar, in the sense that you could perhaps even allow 3 levels, right? That is positive, 0 as well as negative, right? The polar waveform sometimes is also known as non-return to 0 waveforms, because you are always switching back between positive and negative voltages and never really transmitting 0 voltages. In bipolar waveforms, the difference is that you may be also sometimes transmitting 0 voltages, right? So that is the essential. Bipolar and bipolar are very similar in the sense that both have positive and negative voltages, but in bipolar you may also have some durations over which some 0 voltage is being transmitted. But we look at the details as to how that comes about in a few minutes. Let's take the so-called polar waveform, because as far as the choice between unipolar and polar is concerned, it is quite obvious that a polar waveform will be a better choice. Is it obvious to everybody? A unipolar waveform will always end up transmitting some DC voltage, right? That means you are transmitting some power, or you are having some power in the DC component, and by the very nature of information, any constant valued signal has no information content, right? So you are basically wasting a lot of transmitter power in conveying no information whatsoever.
In unipolar?
In unipolar.
But zero is but you are not transmitting power.
No, you are transmitting power at DC, which usually contains no information.
So one is, how do you talk about 0 level as transmitting power?
No. Okay, I think you need. I thought it was obvious, but perhaps it is not.
Everything is zero, so
Average power will be.
If you have some waveform which goes between some 0 level and plus 5 volt, what will be the average value of this? It will be some positive value, right? You will have finite DC component always sitting on the line, which will not be conveying any information, right? And of course it's even otherwise bad to have a DC component for various other reasons which we'll soon discuss. So a unipolar waveform is very rarely, if at all, ever used, right, because of the DC component that is inherently built into such a waveform. So really most of the time we are talking about polar and bipolar waveforms, and we shall really consider those in detail here. Take now the case of bipolar waveforms, like that. That will be typically bipolar waveforms. For example, if you have a sequence 1, 0, 0, 1, you will polar waveform, you will be transmitting a waveform like that. You will be always switching between a positive value, positive voltage, and a negative voltage, never really going through a 0 except for a transition through the 0, right? And therefore this waveform is more popularly known by the name of non-return to 0 waveform, NRZ waveform, right? NRZ standing for non-return to 0. That's a common terminology used to talk about this waveform. All right. Let us see what happens if such a waveform is transmitted onto a typical cable system. For example, ultimately all your waveforms are going to go through some kind of a transmission line, which could be a cable, a pair of wires, or any other communication medium. Now what we will see is that such a waveform is not really suitable for transmission on such a line. The reason why it is not suitable is that most of these cables or systems will ultimately in between, in fact we know will definitely have repeaters in between, right? And at the point at which a cable is connected to a repeater, usually there will be an AC coupling. It will not be a DC coupled thing, because you don't want DC interferences or DC other signals to somehow get in, right? So there will be invariably some AC coupling at the point of a repeater. A cable is connected to a repeater. There could also be transformers in between. It's totally unavoidable to get rid of components like transformers and AC couplings. And typically because of the presence of these kinds of devices on the line, the low frequency response of the line is usually poor, right? Because AC coupling will create poor low frequency response, isn't it? You have done frequency response of RC coupled amplifiers. When there is a series coupling capacitor, it results in poor low frequency response. Similarly, a transformer will result in a poor low frequency response. Just again to couple a signal from one point to another point within the repeater somewhere, you will require a transformer. Typically you will require transformers, right? And therefore the low frequency response becomes very poor. To see the effect of this poor low frequency response, let us look at this pair of waveforms. Let's say this is your NRZ waveform that you are transmitting, right? Corresponding to a sequence 1 0 1 0 1 0. Typically that is the kind of response you are going to get, right? Because of poor low frequency response, you get a droop in the pulse duration. I mean, you get a pulse amplitude is not constant at the output. Let's say you are passing through a coupling like that, right? A series coupling circuit like that, some CR, right? The output of this will typically look like this. I'm sure it is obvious to all of you that is how it will be. So, well, what will be the problem of such a waveform? The problem will come here when I suddenly having a long sequence of ones, let us say a series of ones, right? So you will get a response like that, right? and after that you will get a jump of 2 volts here, right, because when suddenly a transition comes, the the capacitor will just respond by creating the same kind of jump in the output, and you will get now a set of pulses which look the same as these pulses, but there is a difference. What is the difference? The DC level of these pulses is different from the DC level of these pulses. This effect is called a DC wander.
DC answer?
Wandering of the DC level, right? Your DC level is constantly changing depending on when you get a sequence of ones, a long sequence of ones, you will get a drop in the DC level. If you get suddenly a long sequence of zeros, minus V's, you will get a lifting of the DC level, and depending on what is the length of the sequence, the amount by which this wander takes place will keep on changing, right? Now this will create a lot of problems for us when eventually at the receiver or at the repeater we are interested in finding out when we transmitted a 1 and when we transmitted a 0. Remember we talked about match filtering for that purpose, right? But let's forget about match filtering. What is a common sense way of, intuitively appealing way of deciding whether in a particular bit interval a 1 or a 0 was transmitted for such a waveform in the presence of noise? No.
Zero comparison.
The best way would be to look at the area of each pulse, right? The most intuitively obvious way would be, because you don't want to get affected by spikes of noise. So best thing is to average out the noise by looking at not the instantaneous values of the pulse, but by looking at the area of each pulse, area under each pulse, right? If you get a positive area, I mean in this sense, if you get a area which is largely positive, you can declare that if 1 was transmitted. If on the other hand you finding the area is mostly under this thing, under 0 or negative area, you will declare a 0 was transmitted. So this is required to be done at the repeater, repeater after repeater, and finally also at the receiver. Well, actually this is a very simple intuitive way I have suggested. A better way is to do match filtering. We will talk about match filtering later.
How do you look at the area by integrating
Basically that, yeah.
capacitor charge?
Any kind of method for calculating the area will be fine, right? So we will not go into that. Yes.
So you said the problem of DC wander. It is like before we said we want to avoid the DC components in the signal, right?
Right.
So therefore, any variation in that, from that point of view, shouldn't affect, because only the AC power is getting coupled. However, I mean the only thing in which it can affect would be that the threshold can come down. Like one other certain threshold.
No, there are two ways the problem will crop up. I am first describing the first problem, and then the second problem is still the one which we discussed earlier, namely because there is a constant change in DC, and therefore effectively there is always some DC or the other component, which is a waste of power. So eventually you end up transmitting more power for same performance, right? Your power is being wasted here and there, right? So that problem stays. But in addition to that problem, I am referring to a more serious problem here, which I am talking about. We'll just talk about that first.
So what exactly is the method of generating the positive and the negative ones? That will, I mean, how are you so sure that you won't be transmitting any power?
I didn't get your question.
So what I mean to say is that, I mean, it's not very intuitive that you will be transmitting. It depends on how you are generating the positive and the negative.
And what are the voltage current relationships?
For finding the area?
Yes, sir. No. I'm asking you how exactly do you transmit the positive and the negative levels?
This is what we are transmitting. This is the
How do you
transmit.
generate them?
Oh, come on. Does that require any elaboration? How do you generate such pulse strengths?
No, so how do we say that the power,
Power is just what the voltage is like this. So like, what we are arguing out is, since the voltage signal is like this, the power signal.
I have not talked about power in general. I am only talking about DC component. I am not.
You linked the power to the DC component, indirectly hinting that.
Power.
Okay, if there is a DC component, that DC component will contain some power or not? That is the point.
So you mean to say that ideal case you won't be losing any power at a transmitter?
if I don't have a DC level,
Yeah.
that means
I don't lose.
I am all the power that is there in this signal is not being used for transmitting a non-varying component. If you have a DC power, that means some power is being transmitted for conveying a non-varying component, a DC component,
Should get
which is of no use to us, right? That's all that I'm saying. That is you're referring to the old DC problem as to why DC is not a desirable thing to have.
Basically, you mean in the transmitted signal, the DC signal is 0, but now because of that decay, some DC value pops up.
That's
the
right.
problem we're
That's right. The DC level is in fact not only cropping up, it's constantly changing. There are two things. It's cropping up, and secondly it is changing. It is not constant. At least the unipolar case, if this problem was not there, even there this problem will be there. We were talking about a constant DC level, but here the DC level is even changing with time.
There, then it's varying. How will it deteriorate the?
You have not let me complete what I wanted to say. Maybe you would have known if you had let me complete. Right? Okay, so let's come back to what I was trying to say. Detection of ones and zeros. That's what we are talking about. Intuitive way of finding out at the repeater or at the receiver whether in a particular bit interval the transmitted bit value was 1 or 0, and we decided that one intuitively appealing way of carrying out this decision would be, making this decision would be to look at the area under the pulse in that bit duration. For a positive area larger than a certain value, we can always declare safely that a 1 was transmitted. Similarly, for a negative area larger than certain value, we could declare that a 0 was transmitted. Even in the presence of noise, we will be reasonably sure to make correct decisions if we do things like that, because we will not be affected too much by occasional large amplitudes of noise, right, which typically will occur for very short durations, right. So therefore in this kind of a situation, things are fine where the positive and negative areas are nearly equal, right, and your thresholds are usually fixed. Let me complete, please. Right. Now what happens here? Particularly towards the end of this, you have a very small positive voltage in a particular bit interval. Let's say this bit interval. You are trying to decide between this interval, and it may well be that the area here may be below the threshold value which you have decided for a proper decision, right? This may be in fact, because of noise, may look like a negative area, because noise may be largely negative in this region, and the net area may turn out to be negative, and you may take a wrong decision, make a wrong decision. It's possible, because therefore your tolerance to noise becomes very, very small in this particular region. And what is worse, it is unpredictable over time where this is going to happen and where it is not going to happen, right? So this is going to create a lot of problems for us. Is it clear?
So if we have a high frequency channel, and a high number
The channel has a lot of bandwidth, right? In fact, because we have a lot of bandwidth, we are transmitting digitally.
whereas if you have a very high number, the rate of bits is very high, that is the frequency, then the decay problem may not be as prominent, because the amount of time is
No, when we have a large bandwidth, we also have a fairly
have a series of 1 anyway.
series of ones. We can have over fairly large duration.
You see the probability of series of ones occurring is very less.
No,
It's
very,
not-
very, very long series of ones.
not only that, but as the frequency increases, the degrading effect of the series of 1 will decrease.
No, it's like this. It basically depends on the time constant relative to the bit duration,
Bit duration, so
right? That is, so we have to examine that. More importantly, it is important to realize that this is not a very uncommon occurrence. Reason is, suppose you're talking, right? Particularly, let's talk about a series of zeros, right? There could be, if a zero is representing a silence interval, for example, typically there could be long silence intervals in between your words, in between your spoken words, and that could be sufficiently long to cause this DC water, right, and affect your performance. And mind you, remember that at the receiver, we are not talking of a very strong received signal or the repeater. We already have undergone a lot of attenuation, right? So the signal and noise levels that we are looking at are fairly similar to each other. Signal to noise ratio is not infinity, it's more like 10 to 20 dBs, right, or 30 dBs, not much more than that, maybe even down to very close to 0 dB sometimes, right, depending on the situation. So therefore these problems become very prominent. Any other questions on any other discussion you want to have on this?
Width is increased and noise problem will be there.
If width is increased,
Pulse width.
yeah, but if your pulse width is increased, you are sacrificing your data rate. That's the trade-off between your data rate and, you know.
So, but more than pulse width will actually accentuate the DC wander. Like it won't stop the DC wander anyway.
DC wander will not be stopped.
It will be
In fact, it will become more serious. You are right. All right. So if this point is understood, what we can conclude from this discussion is that there are a lot of potential problems in transmitting NRZ kind of signals that is coding the ones and zeros in the form of NRZ waveforms on a transmission line, particularly when there is a long string of zeros or a long string of ones, right? Because line would appear to be either permanently on for some time or permanently off for some time, and that will create problem, because that creates a DC condition which is undesirable. So net effects of this DC condition are, we have discussed these now. I am just summarizing what we have discussed. Our overall power requirement may go up, right, that is one effect. And usually because of poor low frequency response, DC components are also greatly attenuated. Attenuation is greater for DC as opposed to AC. And detection probability or correct decision probability may reduce, or performance may go down, right. Finally, one more effect that I should have talked about, I will just first mention it and then show you the picture again. You may also have the possibility of losing synchronization. Let me talk about this also, this effect. If you get a long string of ones, it's also bad from the point of view of your synchronizer at the receiver. The synchronizer at the receiver or the repeater is going to look at synchronizing information, that is your bit period, from the zero crossings of the received waveform, right. How often ones are changing to zeros and zeros are changing to ones, and that is going to give it some idea as to how to adjust itself so as to be in synchronism with the received bit rate, received clock, right. And when you have a long string of ones or a long string of zeros, it's not going to get those bit transitions for adjusting itself accurately enough. You may be slightly not very confident about what I am saying here, because we have not looked at how a synchronizer really works. But obviously, whatever be the exact mechanism of this synchronization that we will probably study later, it has to derive the information about bits by looking at bit transitions, right, because that is related to clock transitions, right. If it does not get any transitions, it does not get that information, and therefore it may lose synchronization, and that is again bad. That means your local clock may get disadjusted with respect to the received signal clock, and then you are not even looking at the correct bit interval. He will be slightly offset. Instead of looking at this area, he will be looking at this area under this duration, right? Which is even worse, because your local clock has got disadjusted after such a long string of ones. Right? Does it make sense what I am saying? Everybody?
Yes.
Okay. So that's another possible problem, source of problem from a long string of ones that may be received. And obviously the problem gets worse as the length of this all one sequence and all zero sequence increases. The solution to all these problems is the use of properly designed line codes. Okay, that is, use waveforms to represent your binary sequence such a way such that these problems are minimized, if not totally eliminated. Right? Ideally, we would like to eliminate them, but at least we like to minimize them. And there are a number of line codes. We will discuss quite a few of them over here. But let me first talk generally about two important classes of line codes which have kind of been standardized by CCITT, and these are, one code is called the AMI code, stands for alternate mark inversion. And the other one is called HDB N code, right? So this is one and this is the second. HDB stands for high density bipolar. High density bipolar. And N is a parameter of the code. Okay? The basic name is high density bipolar, and N is a parameter of the code which we will talk about. For example, we could have HDB3, HDB5 and so on. Let me talk about these codes and appreciate how the use of these codes avoids or possibly reduces the effect of some of the kinds that we have discussed just now. This picture shows what we do in these situations. The AMI approach takes a simplistic view that if I have a long string of, okay, before I come to the details, one common feature of both these codes is that they are actually both bipolar. That is, they are actually transmitting not only plus voltage level and negative voltage levels, but also zero voltage levels. So in a sense, we can call them as ternary codes rather than binary codes, right? They are ternary codes. They are both ternary. Ternary meaning 3 level. And in both these codes, a 1 is represented either by a positive level or by a negative level, right? Positive and negative levels now are not representing ones and zeros. They are both representing ones, and the zeros are being represented by a 0 level in both these codes. That is one difference. All right. So this is one thing which is common to both. Now in the AMI, one takes a simplistic view that if you get a long string of ones, to ensure that there is no long string of ones, you just alternately invert the ones, right? Alternate marks or alternate ones are simply inverted. That is, if one is represented by plus voltage, positive voltage, the next one will be negative voltage, the next one will be positive voltage, and so on and so forth. And obviously that will avoid a long string of ones. A long string of, actually what you are not worried about is a long string of ones. What you are really worried about is a long positive voltage, a long duration of positive voltage or a long duration of negative voltage, which is what you are really avoiding, want to avoid, which you can avoid by doing things like that. So this is an example. you have this possible sequence in which I have a long string of zeros, which I want to avoid. Right? Actually, AMI will not take care of a long string of zeros. It will only take care of a long string of ones. That is the disadvantage of AMI, which is obvious now. Right? 2 ones it takes care of. First one is like that, 0 is like that. Next one will be like this, because this was a positive one. This is represented by a negative voltage, again by a positive voltage. Long string of zeros goes as such. This is wrong. Thanks. It should have been like that.
So what happens if there is a long string of zeros? I mean,
So
what's the
what's the
disadvantage?
problem? Since the
Long
nothing
string
will
of zero
transmit
won't
it.
cause problem. Because it is a zero level.
So a noise problem of any
What is that? A long string of zeros will also cause.
So
Okay, this is better than
Synchronization problem.
this is better than a long string of negative voltage. Right?
positive one. So
But it is bad for synchronization. Right? So it avoids the DC Wonder problem, but it doesn't totally eliminate the loss of synchronization problem. Right?
So you can't rely on the clock once starting agreeing upon a common frequency and then no synchronization. You need to synchronize it again and again.
Unfortunately, your clocks at various intervals, they will have their own stability equations. Right? They will not really be. In fact, every time you start transmission, one doesn't know whether your clocks are really fully synchronized or not. Even a 1 Hertz difference in clock can be crucially affecting your performance, and it's bad. Right? So one has to be very. That is the cost you are paying in all digital systems. Your complexity is much more than in analog systems. Right? You see, this feature is totally not required in analog receivers. There is no concept of a clock there, and the clock being synchronized with the transmitter clock. Whereas in digital transmission, it is absolutely crucial, right? And there is nothing you can do about it, except to make sure that you satisfy the requirements. All right, is that okay? What is your question?
So not a question. So why don't we have a single worldwide clock?
Yeah, we can have all those things. I think we'll discuss in a different place.
What are the questions?
A universal worldwide clock, right?
You need to have atomic clocks and everything.
Those things already exist, but we are talking of digital transmission in a variety of situations by a variety of people, and everybody wants to do things in his own way, right? So in this Babel of Tower kind of situation, it will be very difficult to do that. Everybody talks about different languages, and therefore this is a slightly let's say utopian kind of thing to ask for this kind of application. Coming to the HDB3, it is very similar to alternate mark inversion with one difference. You also take care of long string of zeros because that is bad, right? What you do is, in fact, the significance of this number 3 or number n is, this is the maximum length of zero string you will permit, after which you will change the nature of a 0 from 0 to 1 in a manner that at the receiver you will know somehow that a 0 was transmitted. Actually a 0 is to be interpreted, right? And the way to do it is, if you get a long string of zeros, follow it up by a mark, but follow it up by a mark of a different rule than the one which you are using in AMI, because you do a violation of that rule, right? Violation being, see, this mark should have been really of this sign, right? But you transmit a mark of the same sign. So when you get two consecutive marks which are of the same sign, the next one is to be treated as a 0.
So if there is still longer, then you will again come back to 0 then.
Right, obviously. You at any time you can permit 3, transmit a mark in between, then again at the most permit 3, and so on. Right? So as long as you keep getting marks of the same polarity, that means they are all zeros. Right? And basically what you are getting is additional 0 crossings, additional bit transitions to take care of your synchronization problem. and in HDBN you can permit up to n zeros, but obviously the smaller the value of n, the better, right? Therefore HDB3 is in fact the most important code out of the HDBN class. So that is as far as these two important class of codes is concerned.
Sir, as far as construction is concerned, I mean, would the HP3 different from HPN? I mean, will the construction of different ends be different, radically different?
By construction you mean the encoder and decoder?
Yes, sir.
They will be similar in philosophy, but the details will certainly be different.
So, but then HB3, why don't we apply the minimum number?
That's right. That's why we mostly use HDB3. The reason is not from the implementation point of view, but from the point of view that you like to have as large number of transitions as possible, as frequently as possible. So n equal to 3 is the most popular HDB encode, right? Because and of course you will require a certain amount of delay here at the encoder, because you will have to see that 3 zeros have come and only then you will do that, right? So a coding delay is implicit in this kind of thing. It will be a good exercise for you to do. Try to design the encoder and decoder for both AMI and HDB codes. I'll like you to do that as an exercise.
In the lab.
Well, do it on your, even if you are not doing it in the lab. All of you please do it. It will be a good exercise in your both your digital logic that you have learned, as well as you can then use it in the lab if you so desire as a project. Any further discussion you want on this? Okay. So basically what we are saying is that data can be transmitted onto a digital line or a cable by using different kinds of line codes, right? Polar, bipolar, on-off or unipolar are the same kind of thing, and it will be useful also to study their spectral properties. There are a lot of nice things we can learn by looking at their spectral properties, looking at their power spectra of signals using different kinds of line coding schemes. So let us spend some time on doing some maths for looking at the power spectrum of such line coded signals. How much time we have? Only about 10 minutes. I'll just start some basic idea about it, how to go about it, and then we'll complete the exercise next time. Now, all line codes are special cases of a pulse train of the following kind. I am taking a fairly general situation here now, where I am permitting even amplitudes to be variable, multiple amplitudes possibly. Right? So I am permitting positive values, positive discrete values, negative discrete values, and also zero values, right, in this general scheme of things. This is your time axis. Let's say your pulse width is some t0, and let's say your these are your new pulse intervals, right? So this may be time interval, this may be time kt0, where t0 is your interval between successive bits, right? So I'm now here having a general situation where even your pulse width may not be equal to t0, it may be less than t0, and this will be k minus 1 t0, this is k t0, this will be k plus 1 t0, right? So one can look at what data is being transmitted. That data will decide the amplitudes of these pulses somehow, either directly or indirectly, and then one can compute the spectrum of this pulse train. If I take a rectangular pulse train and do this analysis, I can do it by using some kind of Fourier series or autocorrelation analysis. But doing it that way only for rectangular pulses has a disadvantage that if you change your pulse shape from rectangular pulses to some other pulse shapes, you will have to redo the calculation all over again, right? Therefore, it is more convenient and more useful to do first a spectral analysis corresponding to an impulse train like that. Okay. So if this was your xt, this impulse train is being represented by a sequence xt, then at k minus 1 t0 you have this impulse, at k t0 you have this impulse, and so on. Let's say the strengths of these impulses are ak. So this is ak here, ak minus 1 here, and some ak plus 1 here, a sub k plus 1 here, where the values of a sub k minus 1, a sub k plus 1 will depend on the data sequence you are trying to transmit, which could be a multi-valued data sequence, multiple amplitude valued data sequence, but discrete, right?
You removed few impulses.
Have I?
When you
This
come
one
down,
corresponds to this one corresponds to this.
What about the coming
what about the coming down and coming back to zero?
No,
Within a particular.
I am representing this
Whole thing.
whole thing by this impulse, right? That means in this waveform the pulse shape being used is this over this duration. The waveform that you are using over 1 bit duration is not a constant voltage level over the whole duration, but a more general situation like that. This is the waveform being used, pulse wave. Is that okay? It could be, if you so wish, you could have it. You could have a waveform covering the whole duration, right? So, but that will be, this will be the most general situation, which will permit you all kinds of. In fact, not most general. For the rectangular pulse class, this will be the most general. But you could have even have non-rectangular pulses, right? Nothing that says that you must have rectangular pulses. In fact, we will see later that in reality we will not be using rectangular pulses, we will be using other pulse shapes, but we will come to that by and by. Okay. So what we like to do is compute the power spectrum first of a impulse sequence, which would be really a random impulse sequence of some kind, isn't it? Whose amplitudes are some discrete valued random values. Discrete random values, because we don't know what these amplitudes might be. They are going to be governed by the nature of the data that is modulating these impulses. Okay. So if we know the power spectrum of this, one can derive the power spectrum of this very simply. How? By saying that I will pass this impulse sequence through a filter whose impulse response is, let's say this pulse shape is pt. So obviously if I pass this impulse sequence through a filter whose impulse response is pt, what will be the output of this? Yt. Yt will be precisely this, because every impulse that comes along will produce an output at the filter whose shape will be governed by the impulse response pt, right? So this impulse will, suppose your impulse response was this, will create this response. The next impulse will create this response, coming like that, and so on.
So if we multiply xt by train of this pt, won't we get right?
That is essentially impulse.
It will be a convolution of this impulse train with the impulse response. right? And if the duration of the impulse response is less than this period, each impulse response will die out before the next impulse comes, right? And therefore really you will get this kind of a situation, right? And that will be the case for our application. The impulse response duration will obviously be less than t0, right? This impulse response pt will have a duration which is less than t0. It could be more, but at the moment we are considering situations where it is less. Any doubts? So therefore first do the spectral analysis of this, then realizing this relationship between this and this, given Sx omega, the power spectrum of this, I can obtain Sy omega, the power spectrum of this, how?
Modulus of Pf square.
Multiply Sx omega with, take the magnitude square of P omega, and that's how you can derive this. So this is a more general approach, and we'll follow this approach, because this doesn't depend on pulse shape. You compute this, any pulse shape, you just have to compute the corresponding Fourier transform and multiply it with that Fourier transform, right? So we'll take that approach. I think we'll start that next time. Thank you.